a minimal model of autonomous agency from the lens of stochastic thermodynamics, Miguel Aguilera and Xavier Barandiaran.
Yeah. Thanks. PDF, yeah. Yeah. All right, thank you. Okay, so this work started with, well, it's in collaboration with Xavier, and Xavier and I have been discussing about autonomy and agency for years, and most of what's here is mostly an exercise for illustrating some points about discussions we had on the relation between autonomy and agency and thermodynamics. Okay, yes, right, okay. Oh, no. So I have just to pass right?
No.
No, so this is the, okay, but
exactly. It's like, I think if you
why doesn't
doesn't work?
go to the next page?
I think you'll have to do it like this or scroll.
No, it's not.
No. Does it work if you press the down arrow?
It goes like this.
It doesn't look ideal. Try clicking this one, or does it do it slowly then?
Yeah. Okay, yeah, good enough. All right, no problem. Okay, so, well, as many of you know, autonomy and agency are central notions in artificial life, but also in fields like cognitive science. And more recently, there has been a lot of interest in artificial intelligence, and especially with models like LLMs and problems like alignment, and trying to address the question of to which extent some system is a genuine source of its own actions and goals, and how independently it can behave respect to the intent of the designer or respect to the constraints given by evolution or other process that created a process system originally. And something that some idea that's repeated quite often in theory about autonomy and agency is that autonomous agents or living systems or autonomous systems in general are able to maintain an out of equilibrium organization in terms of thermodynamics. For example, metabolically, living systems are sophisticated, far from equilibrium systems, which are composed by complicated dissipative structures that channel energy into work, that produce some constraints like enzymes, membranes, etc., that are able to produce more work. And in this sense, living systems are chemical processes that take matter and energy to sustain structures that allow them to maintain themselves. And they are continuously dependent in these flows from the environment to continuously create more structure, more work that allows them to keep existing as such. And the maintenance of this dissipative out of equilibrium structure is a fundamental aspect of life, of autonomy, and of with also belief of agents. So there is not that many formalizations of this idea. One interesting one is by Bihart in the 2000s, in which he described autonomy in terms of non-equilibrium thermodynamics as the capability to recursively maintain dynamic organized states far from equilibrium. He exemplified this idea with a candle, which continuously needs a supply of fuel and oxygen to maintain its activity. And a candle has some degree of stability. It can maintain this out of equilibrium state for a while until the supply of oxygen or fuel ends, and then it disappears. The out of equilibrium process dies down. Okay, and in contrast, systems next to equilibrium have some kind of stability, which is a different kind of stability, which he calls energy well stability, in which systems are able to maintain states. For example, an equilibrium system, for example, a ferromagnetic material can be magnetized. It can maintain this state robustly in front of perturbations. but it is just there. It's a sort of passive stability in which a system can maintain some state, but it requires no interaction with the environment. It doesn't require a supply of energy or a supply of matter to maintain this state. And so in this sense, this will be an equilibrium stability in comparison to a non-equilibrium stability, which is what Bihar calls an autonomous system. And sorry, I think okay, well, and living systems or more complex adaptive systems have this kind of out of equilibrium stability, but they are able to maintain more complex types of stability in the sense that they can adapt or they can extend this stability so that they are not constrained only by the interactions with the environment, but they can adapt, they can anticipate, they can take actions to sustain this stability for longer and not being less dependent on the environment. All right, so from a very minimalistic conceptual level, we can inspire in theory of autopoiesis, and in action, we can define autonomous agents, a system that are maintained by a network of processes that will tend to decay and extinguish in the absence of an intervention. So they are precarious processes. And the interactions between these processes are able to compensate to this decay and maintain out of equilibrium states. And moreover, these interactions, these processes that can maintain these out of equilibrium states are adaptive in the sense that they can interact with an environment in a way that can anticipate or predict or adapt changes and take actions that somehow maximize or increase the capability to survive for these self-sustained processes. Okay, so with these ideas in mind, we designed, we tried to find, okay, what's the most simple model that can describe this process? And we were inspired by Vittorio, this model by Francisco Varela in this 1988 paper, and later in the book, The Embodied Mind, which is a cellular automaton, which is living in a soup of bits, and these bits that are floating around impact the automata, and they can drive the behavior into one way or another, or the system can show different degrees of stability. So we wanted something at this level of simplicity, but the problem is that in this kind of model, it's difficult to derive a thermodynamic description of the system. So we took another inspiration which is molecular motors. For example, this is the case of a myosin molecular motor, in which the presence of chemical reactions, like here ATP hydrolysis, can allows the system to do work. In this case, the heads of the model are able to generate a force through this ATP hydrolysis and attach and detach from an active filament to walk into a specific direction. So the model is using energy provided by this ATP to move in a directed manner. So somehow combining both ideas, we designed this model, which is a sort of molecular motor, which is living in a soup of bits. So these bits carry some energy, mu. So when the bit is equal to 1, the energy is mu. It carries a free energy mu, and when the bit is equal to 0, there is no energy. So the difference of energy between the two states is mu. And the motor is controlled by another bit, x. And so these bits are here, they can degrade, and they can also change their value with the value of x. And when this one goes to the motor and the 0 goes outside, the motor can move forward and clockwise or counterclockwise in the other case. And the motor is acting against a drag force, F. So it takes, I will explain now, it's a stochastic model, but it takes some energy to move this motor. So depending on the relation between mu and F, the model will be more or less effective into moving the motor clockwise, because there is this resistance in the terms of a drag force. All right. Okay, so we model the system like a molecular motor, and we assume that there is some number of molecules of this energy unit, say. I think in most of the simulations I use 50. So the number of molecules is not so large. So, and the model is subject to thermal fluctuations. So in practice, this is a stochastic model. And since we have an energetic description of the system, we know what's the energy contained by its unit, and we know what's the cost of pushing against this drag force. We can model the physics of the system based on these energy levels, and we describe transitions in the system, for example, the change from state X to state Y in terms of some energy function. And this energy function is described here. It depends on the state of X and the state of this capital A, which is just the sum of all the energy units. So each energy unit has energy mu, and depending on the state of the motor, we will have this F term. And when we calculate the probability of jumping from one state X to one state Y, we just consider so the probability is going to depend on the exponential of the energy difference. So the system is going to be stochastic, but it's going to jump more likely to states that have less energy. All right. Okay, so given that, we can use a local detail balance to calculate different kinds of transition. The probability of degrading units A or spontaneously arising depends on this energy mu. This beta parameter here is just an inverse temperature. The probability of changing the state of the energy unit with the state of the motor, which implies moving the motor forward, depends on the difference between mu and F. So the larger the most energy units have, the easier it is to move the motor. And again, once the energy is inserted into the motor and the motor has moved, the value of X can spontaneously flip, dissipating entropy as a heat, because the motor is pushing against a drag force. So this will generate some dissipation in form of heat. All right, so this is the dynamics of the movement, the model. These are stochastic dynamics, and we can think of this transition going to a lower energy level, moving the motor and coming back. And so it's one of these transitions will have some probability and will have some changes in energy that will lead to dissipation if the model is out of equilibrium. We embodied the model in a very simple environment. So we have a one-dimensional ring, and the model is moving forward and backwards using these energy units, and the movement is going to favor movement forwards if we use energy. And so if we just have this, the model will eventually reach to some equilibrium state where the model has reached detail balance, and there is some sort of the arrow of time disappears, and there is no preferred direction of movement in a sense. So in order to allow out of equilibrium states, we introduce some state, n equals 0, in which we insert a battery which recharges the energy of the agent. So if the agent reaches this point, all of the units, energy units, are set to 1, and the agent is with a full battery. So using an environment like this, so in the first case we just use an environment of size 20. So we analyzed what's the behavior of the agent, and for that we calculated the behavior of the master equation, in which we define the state of the system as X, the sum of energy units A, and the position in the environment N, and we calculate this master equation using Glover dynamics. I cannot explain in detail, but this is the same dynamic rules that I explained before. And we can, since the model is not that large, we have 20 positions and 50 states of the total energy of the system. We can calculate the non-equilibrium steady state distribution of the system after a while. And this is an exact calculation. And what happens is the following: the model starts, or the system can start in position 0 with a lot of energy, and it can advance by expending energy. The movement is stochastic, so you see this blur. And at some point, the model can get to the end of the environment and get to the initial position again, and it will recharge again and go to the first part here. But as the movement is stochastic, some agents will move forward and backwards and eventually lose all of their energy and fall into this area here. And here the model is stochastic, it can still move, but there will be no preferred direction of movement. The model is going to advance forwards and backwards randomly not being able to, or it will be very unlikely to reach the end of the environment and get more energy. And we see that there is these two bumps here. This is just an histogram of the levels of energy. So how can we distinguish between what's happening here and what's happening here? And an easy way to do this is to use tools from stochastic thermodynamics, specifically Crookes fluctuation theorem, to measure what's the level of dissipation of entropy of the system, how far from equilibrium the system is. And if we calculate this, we see that agents with low levels of energy, so agents here, are not dissipating any entropy. They are basically near equilibrium. But models here, systems here, they are dissipating a lot of entropy, so they are very far from equilibrium. So this is a way to describe some kind of intrinsic viability, which is based on the thermodynamics of the system. And just to, okay, so the last thing that we tested is so this is just an autonomous system in a thermodynamical sense, as it is a system out of equilibrium, but does it have some capability of agency or to ensure its own persistence? So we tested about how this agent could be modified to sustain its persistence, and we did the following. We allow the system to redefine what's the size of the steps it takes in this environment. So if there is this drag force resisting my movement, if I take smaller steps, I can use less energy per step as if in comparison with if I take larger steps. And so in that sense, the energy mu that I have is going to make it easier or difficult to advance depending on how large are the steps that I take. So allowing this, we see that if I take steps that are too large or too small, it's very difficult to survive. Most of the agents die. But in the middle, there is an area in which the agent is successful. And just looking at my energy level and what's the average absolute speed, I can know if I'm in this area or this area and modify my behavior to be more effective. And just using this very simple rule, using two thresholds, looking at my energy levels and looking at my absolute speed, I can design a rule that bring any agent back into this viable zone or this area where the out of equilibrium states can be maintained and can be sustained for a long time. So in this sense, we just calculated this threshold, but we could very easily design behaviors or strategies for these agents to be able to sustain themselves in front of the different environments. So here there is, so here we assume that we have different environments with different levels of energy of these energy units. So independently of that, the rule can find behaviors that drive them into the sort of viable state. So just to finish, so we took this idea of autonomous agents as being capable of adaptive interaction with the environment to enhance their capabilities to maintain out of equilibrium states, and we built a simple model to illustrate this idea. And interestingly, even if we are talking about thermodynamics, everything is just measured in terms of bits and in terms of entropies as an information theoretical perspective on thermodynamics, in which at a mesoscale we can describe generalized thermodynamic quantities into an information theoretical measurements. And basically our long-term goal is to extend this idea to energy-based levels, energy-based models like stochastical modeling, or we want to use Hopf field networks, or we are interested also like in this connection between Hopf field networks and transformers, but in which we can describe complex dynamics in terms of energy and in terms of these thermodynamic ideas of sustaining high energy states. But that's really a topic for another year. And future developments could include making environments more complex or try to derive thermodynamic bounds or other bounds on what's the potential capabilities of the agents from their thermodynamic states. So that's all. Thank you.